At the tiniest scales, molecules dance in relentless chaos. Thermal motion jostles atoms randomly, collisions scatter particles in every direction, and the laws of statistical mechanics seem to predict nothing but disorder. Place a drop of dye in water, and it spreads out chaotically, never gathering back together. The second law of thermodynamics tells us that entropy, the measure of disorder, always tends to increase. From this perspective, the universe should be a restless soup, always drifting toward greater randomness. Doesn't it seem puzzling, then, that everywhere we look, we find remarkable patterns of order? Life itself is the clearest example. From the chaos of countless molecular collisions emerges the exquisite order of cells, tissues, organs, and finally consciousness. DNA molecules self-assemble into double helices, proteins fold into precise three-dimensional structures, and cells cooperate to form organisms. These structures are not imposed from outside. They arise naturally out of complex interactions. The trick is that systems far from equilibrium, fueled by energy flows, can spontaneously create order. A cell burns nutrients and channels energy into maintaining its intricate machinery. Could it be that disorder, when combined with energy and rules of interaction, becomes the very source of life's order? On the human scale, order is everywhere we look. Our bodies regulate temperature, heal wounds, and maintain homeostasis in the midst of chaos. Our minds build stable memories out of flickering electrical signals. Even societies, with all their turbulence, generate languages, cultures, and traditions that endure across generations. It is as if order emerges as a property greater than the sum of chaotic parts. How do countless random neurons give rise to something as structured as thought, logic, and self-awarenessness? The cosmos offers an even grander example. After the Big Bang, the universe was filled with hot plasma, a turbulent sea of particles and radiation. Over billions of years, gravity gathered this chaos into galaxies, stars, and planets. Chaotic dust clouds became ordered planetary systems. Within stars, chaotic collisions of nuclei gave rise to stable elements like carbon and oxygen. The very building blocks of life. From formless plasma, cosmic architecture emerged. Galaxies with spiral arms, stars arranged in clusters, and filaments stretching across the universe like a vast cosmic web. Isn't it astonishing that the same random thermal motion that makes molecules jitter can, on a larger scale, seed galaxies? The paradox is that order and chaos are not enemies, but partners. Random fluctuations provide the raw material, while natural laws, gravity, electromagnetism, chemical bonding, channel them into patterns. Entropy still increases overall, but pockets of order can bloom temporarily fed by energy. A candle flame, a snowflake, or a living cell. All are islands of structure in a wider sea of disorder. The deeper insight is that order is not opposed to chaos. It emerges from it. So perhaps the true mystery is not why disorder dominates, but why the universe is so generous in allowing bursts of order to arise, from molecules to minds to galaxies. Could it be that order is the universe's way of making chaos visible? At the microscopic scale, atoms and molecules move randomly due to constant thermal energy. Each particle collides, scatters, and changes trajectory in unpredictable ways, producing apparent disorder. Thermodynamics and statistical mechanics describe this ceaseless agitation as the natural background of matter. Tracking any single particle's exact path is nearly impossible, because even the smallest perturbation alters outcomes. This microscopic chaos seems to preclude stable order at larger scales. Yet it is precisely this ceaseless motion that provides the foundation for emergent regularities. Without molecular chaos, systems could not equilibrate or support higher structures. Gas molecules in a room move chaotically at hundreds of meters per second, yet the room's air pressure remains stable. It is like countless bees buzzing randomly, while the hive as a whole stays intact. When enormous numbers of particles are considered together, randomness averages into stability. Collective behavior produces measurable macroscopic properties such as temperature, pressure, and entropy. Statistical laws emerge, allowing predictions without needing to follow each particle individually. The law of large numbers ensures that random fluctuations cancel, producing reliable averages. This gives the illusion of smoothness and order at higher scales. What looks like chaos in detail becomes predictability in bulk. Physics uses this principle to translate disorder into stable laws of matter. The ideal gas law describes gases accurately without tracking the motion of each molecule. It is like rolling millions of dice. The outcome of each is random, but the average result is always predictable. Grazie a me. Living systems transform molecular randomness into organized structure through self-organization. Proteins, lipids, and nucleic acids diffuse and collide randomly. Yet under proper conditions, they assemble into membranes, enzymes, and genetic frameworks. Chemical affinities and thermodynamic rules guide this assembly, stabilizing structures against dissolution. Feedback loops reinforce useful patterns, allowing cells to persist despite constant molecular collisions. Evolution further exploits randomness, turning mutations into sources of adaptation and complexity. Life therefore thrives on balancing noise with order. Biological order would not exist without chaotic molecular inputs fueling it. Lipid bilayers form spontaneously in water, creating the membranes that define cells. It is like dancers moving randomly until a shared rhythm pulls them into coordinated motion. The brain's neurons fire in noisy, seemingly chaotic patterns influenced by countless chemical and electrical inputs. Each spike of activity is uncertain, but together, billions of neurons generate structured networks of thought and perception. Coherence arises from dynamic feedback loops that stabilize patterns across the noise. Consciousness itself is not about eliminating randomness, but about harnessing it to create adaptability. Randomness contributes to creativity and flexibility, while order ensures continuity of identity. Mental life emerges from the tension between chaotic inputs and stable neural pathways. Human awareness is thus a layered phenomenon built from disorder shaped into order. Functional brain scans show chaotic millisecond activity, but reveal consistent large-scale network, such as the default mode network. It is like static on a radio that, when tuned, resolves into a recognizable broadcast. In its infancy, the universe was filled with a chaotic plasma of particles and radiation. Tiny fluctuations, seeded by quantum uncertainty, disrupted this uniformity. Gravity amplified those fluctuations over billions of years, drawing matter together into stars, galaxies, and clusters. From a turbulent soup, cosmic architecture emerged, producing immense order at vast scales. The cosmic web seen today traces its roots back to these chaotic beginnings. Disorder on the smallest scales became the blueprint of large-scale structure. The cosmos demonstrates that chaos is the seedbed of organization. The slight temperature ripples in the cosmic microwave background grew into galaxies and clusters. It is like random bubbles in bread dough that shape the rise of the entire loaf. Entropy describes the measure of disorder, and the second law of thermodynamics guarantees that total entropy in the universe always increases. Yet, local decreases in entropy, and therefore order, are possible in open systems that exchange energy with their surroundings. Stars, planets, and living organisms maintain order by exporting entropy outward. Earth's biosphere, for instance, uses the sun's energy to sustain complex life while radiating waste heat into space. This creates pockets of order against the universal trend toward disorder. Paradoxically, increasing global chaos allows local islands of structure to persist. The rise of order is therefore deeply tied to the expansion of entropy overall. Plants build ordered molecules by absorbing sunlight, but in the process they increase entropy through heat release. It is like tidying one room by tossing clutter into the hallway. Order emerges locally, while overall disorder grows. Chaos theory shows that deterministic systems can behave unpredictably. Even small changes in initial conditions can lead to vastly different outcomes, as in weather systems. Despite this unpredictability, hidden patterns often emerge in the form of attractors or fractals. These structures show that chaos is not pure randomness, but structured unpredictability. Stability and disorder intertwine, revealing complex order behind apparent noise. Chaos theory proves that order often hides inside irregularity. It reveals that nature's unpredictability is patterned at deeper levels. The Lorentz attractor produces chaotic motions that nonetheless trace a repeating, butterfly-shaped pattern. It is like smoke, rising unpredictably, yet always curling into recognizable spirals. Human technology exploits both order and randomness. Randomness provides unpredictability for encryption, while order ensures reliable engineering in machines and devices. Quantum mechanics supplies noise and uncertainty, yet semiconductors and circuits channel them into predictable outputs. Engineers design systems that tolerate chaos while preserving stable operation. In some cases, chaos is deliberately harnessed to generate novelty or secure communication. Progress depends on carefully balancing these two forces. Technology thrives by transforming noise into function and structure. Thermal noise in electronics is used to generate truly random numbers for secure cryptography. It is like flying a kite. The chaotic wind gives energy, but the string provides control. The paradox is that chaos is not the enemy of order, but its engine. Disorder supplies variability, while forces like gravity, chemistry, and feedback loops channel it into structure. From molecules to galaxies, patterns are born from turbulence. Random collisions give rise to thermodynamic stability, neural storms produce thoughts, and cosmic fluctuations shape galaxies. Without chaos, order could never form. Without order, chaos would lack meaning. The universe is built from their inseparable interplay. Chaos and order are not opposites, but partners in complexity. Galaxies with elegant spiral arms grew out of the chaotic plasma of the early universe. It is like jazz improvisation. What seems chaotic resolves into higher harmony.